Okay, we were discussing conditional probability in the last class. So we've seen that the probability of event B given event A has occurred is given by probability of A intersection B over probability of A. And similarly, probability of A given B is probability of A intersection B over probability of B. Or you can also say that the probability of A intersection B can be written as probability of A into probability of B given A. Okay. In that case, we have seen that the probability of one event can be affected or it can be influenced whether the second event has occurred or not. Okay. And we have taken example of drawing of cards from the deck. So as an example, suppose an experiment consists of drawing two cards from a deck in succession without replacing the first card, and you have to assign a probability of obtaining two red aces in two draws. Okay, so it consists of drawing two cards in succession without replacing the first card, and you have to assign a probability of obtaining two red aces in the two draws. So if you denote the two events with A and B, so A denotes that the first card is a red ace, or you can say that the red ace in first draw, and B events red ace in the second draw. So we basically try to find what is the probability of A intersection B. Okay, that is the probability of finding two red aces in two draws. Okay, so finding the joint probability of A intersection B, that can be taken as probability of A into probability of B given A. Now the first event A, it is basically independent of event B. So probability of A will be 2 by 52, which is 1 by 26. Okay, because we have two red ace out of 52 cards. So probability that in the first draw you get a red ace is 2 by 52, which is 1 by 26. And probability of B given event A. So if the event A has already occurred, it means in the first draw the card is a red ace. The probability of B given A will become 1 by 51. Okay, because in the first draw you have 52 cards and there are two red ace. So the probability that in the first draw you get a red ace is 2 by 52. Okay. Now probability of B given A. Now the first event A has occurred or it has happened. It means in the first draw the card that you get, it is already ace. So you are now left with one ace and 51 cards. So the probability of B given A is 1 by 51. And if you multiply these two, you get 1 by 26 into 1 by 51. Okay, which makes it as 1 by 1326. So this is the joint probability of both the events A and B. Okay. So likewise, you can have many other examples. So conditional probability, and then we had independent events. Okay. So if you have two events A and B, and if the probability of A is not affected by whether event B has occurred or not, then these events are called as independent events. Okay, like suppose in the example of drawing the cards from the deck, so if you replace the first card and you shuffle the deck before drawing the second card, then the probability of the second card or the outcome of the second draw is no way affected by the outcome of the first draw. Okay, in that case the probability of B given event A has occurred is basically same as the probability of B, or probability of A given event B has occurred is same as the probability of A. So the probability of B is independent of whether event A has occurred or not. Okay. Likewise, the probability of A is independent of whether event B has occurred or not. So these are called as independent events, in which the probability of occurrence of one event is not dependent on the occurrence of another event. Okay. Now, if two events A and B are independent, if A and B are independent events, then of course we have already seen that probability of A intersection B, which is given by the probability of A into probability of B given A. And if A and B are independent, then probability of B given A is probability of B, and it can be written as probability of A into probability of B. Okay. So if the joint probability of two events, probability of A intersection B, is equal to the product of their individual probabilities, then we say that these two events are independent. Okay. So in the starting, we have discussed about disjoint events or mutually exclusive. In that case, the probability of A intersection B is phi. A intersection B is phi, or the probability of this is 0. Okay. So disjoint and independent, they are two different things. Okay. In the disjoint, the two events cannot occur at the same time. So if event A occurs, then event B cannot occur. Okay. This means these two events, they are not independent events, definitely. Okay. So likewise, if you suppose uh, throw a coin twice in succession, then the probability of getting a head or a tail in the second trial is independent of the probability of occurrence of head or tail in the first trial. Okay, because these two events, they are not dependent upon each other, so we call them as independent events. Okay. Now, when these events are independent, we have a special, you can say, trial, which we call as Bernoulli trial. So in the Bernoulli trials, the experiment has only two outcomes. So we call it as a success or failure. Okay. We only have two possible outcomes. Okay, which we map to success or failure. So if suppose if a certain event A occurs, then it is a success, and if the probability of suppose that event A is P, then the probability of success is P, and if Q is the probability of failure, then Q will be 1 minus P, of course. Okay. So we will try to find what will be the probability of K success in n Bernoulli trials. Okay, probability of k successes in n trials. Okay, so you have Bernoulli experiment in which the outcome of experiment is limited to 2. Okay, if the event occurs, it is success. If it does not occur, it is failure. Okay, so like suppose you toss a coin, you have only two outcomes, head or tail. So you can suppose map, if the head appears, it is a success, and if the tail appears, it is a failure, and so on. Okay, so if you have a Bernoulli experiment or a Bernoulli trials, so you have only two possible outcomes. So if the event occurs, the probability is P, which is the probability of success, and the probability of failure, of course, is 1 minus P, which is Q. Okay, because sum of both probabilities is 1 by 2. Like the probability of getting head is 1 by 2, and the probability of getting tail is 1 minus 1 by 2, it is also 1 by 2. Okay, so what will be the, if the trial is a Bernoulli trial, what will be the probability that of k success in n trials? Okay, like suppose what is the probability of success of getting 10 heads in 50 tosses, like that. Okay, so n is the total number of trials and k is the number of successes. So what is the probability of getting k successes in n trials, given that the probability of success is P and the probability of failure is 1 minus P. Okay, so this is basically given by n factorial divided by k factorial into n minus k factorial p to the power k into 1 minus p to the power k. So this is taken as the probability of k successes in n trials. Okay, like tossing a coin and observing the number of heads in a Bernoulli trial with probability value of 0.5. So the probability of getting k heads in n tosses will be given by this, where we have to place p with 0.5. So this is 1.5 times k, and this is 0.5 times, this is n minus k, sorry, n minus k. I'll see how you get this relation. Let us suppose that you toss a coin 3 times. Okay, and you observe the number of heads in each outcome. So the possible outcomes can be all the 3 heads, or first 2 head, then 1 tail, or head, tail, head, or tail, tail, tail. Okay, or head, head, tail, tail. You can have tail, head, head, tail, head, tail, or tail, head, head. So you basically have 8 possible outcomes. Okay, now if you see their probabilities, so number of success, if I write here number of success is 3, because I am basically observing the number of heads, okay, in the 3 successive tosses. So if you get all 3 heads, number of success is 3. In this case, number of success is 2. Then number of successes here is also head, tail, head, here 2. Then we have 1. Then we have 0, all the 3 tails. Then we have again tail, head, It should be tail, tail, head, tail, tail, and head 1. Then tail, head, tail 1, and tail, head, and head we have 2. Okay. So you have 3 successes in this case. In this case, you have only 2 successes. In this case, again 2. In this case, again 2. Okay. So if you just see the probability of getting 3 successes, that will be 1 by 8, because we have 8 possible outcomes, and out of the 8 outcomes you have only one combination in which you have 3 heads, so it is 1 by 8. Okay, so probability of getting 2 heads, in that case you have 3 by 8, because you have 3 such combinations which can generate 2 heads. Okay, although they are not in specific order, the order can be anything. So this probability of 2 heads is 3 by 8. Probability of 1 head, probability of getting 1 head. So in case of 1 head, you have again 3 by 8. This one, and this one. And probability of getting 0 heads is again 1 by 8. Okay. So if I write in terms of, if I compare this with terms of this equation, the probability of getting, suppose, k successes in n trials, okay, and I have performed 3 trials, and out of 3 trials if I want to get 3 successes, so probability of 3 successes in 3 trials, so k is 3, n is 3, you get it as n factorial, that is 3 factorial divided by 3 factorial into 0 factorial, which is 1, into p to the power k 3 into 1 minus p to the power 0, and in this case the probability is 1 by 2. Okay, because I'm tossing a coin, the probability of success is 1 by 2 and the probability of failure is also 1 by 2. So this basically becomes 1 by 2 into 1 by 2 into 1 by 2. This is this term. Okay, so if we have k successes, definitely we'll have n minus k failures. Okay, so the total probability will be p to the power k into 1 minus p to the power n minus k. But this comes into the picture because you have more than one combinations which gives the same success rate. Okay, so that is why we have this factor here. So if you solve this, it becomes 1 by 2 to the power 3, this gets cancelled, and to 1 by 2 to the power 0, and you get it as 1 by 8. Okay, likewise the probability of getting 2 successes in 3 trials, that will be equal to, now n in this case is 3, so 3 factorial divided by 2 factorial into 1 factorial into 0.5 or 1 by 2 to the power k, k is 2, into 1 by 2 to the power n minus k, that is 3 minus 2, it is 1. So this 3 factorial becomes 3 into 2 factorial, and this gets cancelled, you get 3 into 1 by 8. Okay, so the probability of 3 getting 3 success in 3 trials is 1 by 8, because that is simply p to the power k into 1 minus p to the power n minus k, and in this case this term becomes 1. You get p to the power 3, which is 1 by 8. Probability of getting 2 success, which is 3 by 8, just we have seen here. Probability of getting 1 success is again 3 by 8. Using the sum you can prove, and probability of getting 0 success is again 1 by 8. Okay, so this is a special trial or experiment which is called as the Bernoulli trial, in which the outcome of the experiment is just classified as success or failure, that whether the event has happened or not. If it has happened, it is a success, and if it has not happened, it is a failure. And if the probability of that success is p, then the probability of failure, of course, is 1 minus p. You only have two probabilities, p and 1 minus p. And if you repeat this experiment n times, that means you have n trials of the Bernoulli experiment, then the probability of getting k successes in n trials is given by this. This is what I have shown here. Okay. So, like suppose we take one example given in the book. You have a binary symmetric channel, BSC channel. It has an error probability PE. This is your error probability. It means error probability means that is the probability of receiving 1 when 0 is transmitted, or if you transmit 1 and you receive 0, this is the probability of error. Okay, or error probability. So you have to determine the probability of receiving exactly k digits in error. Okay, so the probability of, this is the conditional probability. Conditional probability of 0 given 1 is transmitted is equal to probability of 1 given 0 is transmitted as P of k. Definitely, if this is the probability of error, okay, or the probability of failure, you can say, and the probability of success, that is probability of 0 given 0 is transmitted, will be same as the probability of 1 given 1 is transmitted is 1 minus PA. Okay, so this can be taken as a Bernoulli trial. Okay, so you have binary symmetric channel in which the error probability is P. That means if you transmit 0, you receive 1 with the probability of P, or if you transmit 1, you receive 0 with the probability of P. This channel is symmetric with respect to 0 and 1. So probability of 0 given 1 is transmitted, or probability of receiving 1 given 0 is transmitted is P. Definitely the probability of receiving 0 while 0 is transmitted is same as the probability of receiving 1 while 1 is transmitted as 1 minus P. Okay, so the P of Yx, it basically denotes the probability of receiving Y, the probability of receiving Y when X is transmitted. Okay, and the question is that you have a sequence of n binary digits is transmitted over this channel. Okay, a sequence of n binary digits is transmitted over the channel. So what is the probability of receiving exactly k digits in error? Okay, so out of the n digits that you are transmitting over this channel, the probability of getting k digits in error is definitely n factorial divided by k factorial into n minus k factorial, p to the power k into 1 minus p to the power n minus k. Okay, So the reception of each digit is independent of other digit. Okay, all the trials, they are basically independent. So this is a example of Bernoulli trial with probability of success is equal to P, that is the success here is receiving a digit in error. Okay, clearly the probability of k successes in n trials or k errors in n digits is given by this relation. Okay, so for example, if your probability error is 10 to the power minus 5, then the probability of receiving 2 digits wrong in a sequence of 8 digits will be 8 factorial divided by 2 factorial into 6 factorial into 10 to the power minus 5 to the power 2 into 1 minus 10 to the power minus 5 to the power 6. Okay, which is approximately taken as 2.8 into 10 to the power minus 9. Okay, so this is the probability of error. It means out of 10 to the power 5 bits that you are transmitting, there is a probability that 1 bit will be in error. Okay, that is the meaning of this 10 to the power minus 5. So the probability of receiving 2 digits wrong in a sequence of 8 digits will be given by this. Okay.